Since we didn't have time in class to go over representing each of these different scenarios, I wanted to make this recording. So when first we're talking about multiplying a fraction by a whole number, we can see these two different cases. This case of, right, this on the left, we're talking about 3/5 of 200. So this idea of scaling, or we can see it as this repeated addition, especially when it's multiplying by a small number. We can still see it as repeated addition here, but 3/5 200 times is going to be a lot. So this, we can think about it as this idea of scaling, taking 3/5 of 200, right? We don't want a whole 200. And so one way we can represent that is through the idea of the area model of a grid. So here's a grid. This is like an online grid that I could find that you could fill in. And so if this is our 200, whatever it is, we can think about taking 3/5 of that. And so we can see here, I marked it where we can have 1/5, 2/5, 3/5 of that. And now we can fill that in, and we can see this area of 3/5 of this 200. So that's one way we can think about it. Let's see, we can also think about it. Sorry, I wanted to clear that. We can also think about it as, oh, the apple, let me do that. Well, on the computer, so we can, on the computer, you can do a circle with 200 slices. I'm on the iPad and the app won't let me do that. And then we can compare then the areas of 3/5 of one circle, put that on top of the circle that's cut into 200 pieces, and then we can shade out that exact same area. Another way we can think about it is, on a number line, if we're going to 200, we can think about dividing this into 1, 2, 3, 4, right? 5 equal parts, and we want 3 of them, right? 3/5 of my 200. So that's kind of also like a length model. And so this fraction times a whole number can be seen in a number of ways. And as many others saw with the other question, when it was 3 times 5, 6, right? We can see this as, 5, 6 one time, 5, 6 two times, 5, 6 three times, in the area model. We can see that on the number line. I didn't think. Sorry again. There we go. And then so we can see the same idea. We can do 5, 6 one time, 5, 6 another time, 5, 6 another time. And so we can see with these hops on the number line, we see, right, it ends us at 2.5. So this is our 3 times 5 6. And this is the same as, or 2 and 3 6, right? 2 and 3 6. And so this is either, right, 5 halves, or 6 times 2, 15 sixths. And if you think about the algorithm, right, the procedure, 3 times 5 would be 15 sixths. So these are all the same. And how, right, we can use the models, the representations, to find the product in this case, right, it's multiplication. And then by seeing this, each of these products, like time after time after time, that's how we can begin to develop the reasoning for the algorithms, or for the procedures. So that's how we want to go about it. We want to use the the representations to help show why and how these work. So we start with the representations and then we build to the procedures and say, hey, look at this and look at, and how do you think, we can just look at the numbers to get these numbers. All right, I'm going to clear all of this. Now, what I also want you to think about is this idea, right? We had 3 times 5, 6, but that's the same as 5, 6 times 3, right? This is the commutative property. So just like with our, 3/5 of 200, we can think about this as 5/6 of 3, right? So this one was, right, 5, 6, 3 times. You can see either of them in that way, or we can see this as 5/6 of 3. So that means I want to, sorry, this is not looking nice. I want to take this 3 and I want to cut it into 6 equal pieces, right? That's what the denominator tells us to do. Cut into 6 equal pieces. And then the numerator tells us how many of those pieces we want. So if we think about cutting it into 6 equal pieces, we want all the way to 3. And so you can think about 3 as, right, 18/6. And then therefore, right, to cut this into 6 equal pieces, we want 1, 2, 3, 4, 5. So we want each piece to be, right, length 3 or 3, right, 3/6, 3 tick marks long. Or you could have counted, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right? We could have counted all of those tick marks to know how to partition it, how to divide it, right? So this is that connection to whole numbers. So now we know, right, each sixth, so this is, right, 3/6 or 1/6 of 3 is another way to think about that. And now we said we wanted 5. So we want 1/6, 2/6, 3/6, 4/6, 5/6, right? 5/6 of 3 is 2.5, 2 3/6, right? Just like we just said when we did the repeated addition of 1 time, 2 times, 3 times. So now for the next example, we have 1/3 of a half. So we can think again about the area model, have our garden, we're going to cut it in half. So here's half for the herbs, here's half for the veggies. Sorry, that might have been, I'll bring this. Half for the herbs, half for the veggies. And now I want, right, 1/3 of my half. So I want to take each half and cut it into thirds, right? So now one herb or one veggie gets 1/3 of a half, right? Cut your half into 3 equal pieces, right? 3 equal pieces. And then so equals, right, 1/6 of the whole, 1 out of 6 pieces here. And so this is still the area model. We're just using the shape of a rectangle in this case, and we're looking at the space, right, this piece takes up. We can see this also, right, with those overlapping rectangles in our asynchronous lesson. Similar idea, but we'll connect it to our week 13 tasks, right? If we think about 2 1/3 cup, or 2 1/3 times 3.5, well, we can think about this using the distributive property, right? Each of these fractions actually has an addition problem inside of it. So again, we can think about it as an area or an open array. 2 plus 1/3, and then 3 plus 1/2, and we can do this multiplication. And again, there is a virtual manipulative in your asynchronous Nearpod for you to check out. Sorry. For you to check out, this overlapping areas in this instance. I also want to show the 2 1/3 times 3 1/2. Oh, sorry, it's kind of ugly looking. With the set model, because I know that one's particularly tricky. And so what we're thinking about when we're multiplying fractions or even dividing fractions or adding, right, is this idea of creating a set that can show both denominators. So again, we want to show both thirds and halves. So we can create our set as, right, 6, where you can see thirds and vertically and halves horizontally. And so what we think about, if this is 1, how do I show 2 1/3? So I can show 1, this is 1 whole, this is a third. So this is, and this is another whole. So here I have 1, 2, and a third, right? 1, 1, 1/3. So now if we think about either this idea of times, like how 2 1/3, this is 2 1/3, 3 1/2 times. So we can do this 1 time. We can do this 2 times. We can do this 3 times. And now we also want it 1/2 of a time. So we can take this, and I'll do this in another color. So we can take this 2 1/3 and cut it in half. Oops, sorry. So, and maybe I'll do that down here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2. So now what we want to do, so this is 2 1/3, and now we want half. Oopsie, not a T. That's an L. We want half of it. So we take half of it. So we have 2 1/3 1 time, 2 1/3 2 times, 2 1/3 3 times, and now we have it 1/2, right? 1/2 of a time. And so that looks like, actually, maybe I'll do this in blue. Keep it all consistent, right? Right, kind of take that top row of each of these here. So now we can see, now we can start to count. These are all of our dots. And we're like, all right, what in the world is going on? So we can see that this is, right, 1 hole, 2 holes, 3 holes, 4 holes, 5, 6, 7. So we have 7 holes. And now we have 1/3, 2/3, 3/3, 4/3. Sorry, 1/3, 2/3, 3/3, plus 3/3, and then plus, what is this little guy? 1/6. And so we can connect that to, right, our 3 1/2, our 2 1/3, right? 2 times 3 is 6. 2 times 1/2 is our 1. 3 times 1/3 is a whole, and then 1/2 times 1/3 is our 1/6. So we see we have 6, right? 6, 7, 8, and a 6. We have 7 holes plus another hole equals 8 and a 6th. So we can see this multiplication if we think about it as how many times, or you can think about it, or sorry, how many times, and we just duplicate that set, right? This set of 2.5, 3 times, and then a half of a time. So likewise, we can show that on our number line, right? We want 2.5, 1 time, 2 times, 3 times, and then if we did 4 times, we'd end up all the way there, but we don't want a whole time. We want, right, a half of a time. So that would be, oh, and sorry, I just looked 2.1/3 times 3.5. So I did 2.5 times 3.5. So that's why it wasn't the same. So let's delete this guy. Let's delete this guy and come back. Let's leave that guy. Come back here. We don't want 2.5. We want 2. We want 2.1/3. 2 and 2, 6. Now 1 time, 2 times, 3 times, and now a half of this time. If we look here, right, we can take from here to here, cut this in half, and I'll clear that space, right? And that's how we get 2.1/3, 3.5 times, right? 1 whole time, jump 2 whole times, jump 3 whole times, and then we want to stop, right? This would be 4 whole times. So we stop here at this 3.5 times. So now let's get into division. In class, remember we talked about this 3/4 of a cup of sugar. How many times, right? How many times does 3/4 cup, right, fit in? Or how many can we take away, right? This idea of repeated subtraction, fit in 3 cups. Or how many 3/4 cup can we take away from 3 cups? So this is that measurement division, repeated subtraction, or how many groups interpretation of division. And so let's see this on the number line here. We're thinking about, here's my 3, right? 3 divided by 3/4. So we want to think, oh, I'm in 6, sorry. Let me change this, fractions, fourths. Okay, I'm gonna clear all the work, no problem. So we want 3 divided by 3/4, and here's our 3. So we're thinking about how many 3/4 long pieces. 1, 2, 3, 4, right? How many 3/4 long pieces fit in, right? 3/4 fit in, 3/4 fit in 1 time, 2 times, 3 times, 4 times. So 3 divided by 3/4 is 4. And wow, what? How does it, right? So this is how we start, right? With example after example after example is how we start to develop this procedure for multiplying by the reciprocal, right? 3/4 goes into 3, or 3/4 3/4 times what number is 3, is another way to think about it. And so this question mark here, right, is that it go 3/4 times what number? 3/4 times 4 is 3. And so that was just one representation with the number line. You can show that again, see the asynchronous lesson for week 13 to show that with the fraction circles, the fraction tiles, it would be the same thing. Let me see if I can get the fraction tiles. Sorry. Fraction strips, right? So we want, we can only do 2 in this one. Well, I guess we can do 3 there. When I think about, here's 1/4. Oh, sorry, let me turn that off. So here's 3/4. We want to see how many times that will fit into all three of these. So there's 1 time, here's 2 times, here's 3 times, and then 1, 2, last time, 4 times. And I can't, maybe I can, no, I can't annotate at this moment, but I will draw it in the slide. And so let's clear this and do the same thing with, actually, we want the next example, sorry. The next example is the same exact idea. 2/3 each show, right? Each is 2/3 of an hour. So the question is, how many shows is the same as how many groups? So we can show that again in the number line or in, and actually we now want thirds, thirds, okay. And so we think about, right, how many 2/3, 1, 2, 3, 4. Uh-oh, right? This didn't go in a whole time, right? We want, no. We want, well, sorry. No, I'm playing. How many 2/3 fit into 2? Sorry. So 2 divided by 2/3. So we only needed to go here, right? So it fits in 1 time, 2 times, 3 times. So we get this again 3 times. So we can think about 2/3 times what number equals 2 is what this is saying. But if we wanted to do 3 divided by 2/3, we still think about 2/3 times what number equals 3. And now maybe it's not so clear. So we can see it goes in 1 time, 2 times, 3 times, 4 times, and then not a whole time, a half of a time. So this 3 divided by 2/3 equals 4.5. Again, so that was the length model. Here we can show that with, sorry, this is another length model. That was the number line clearly. So let's do, right, here's 2. We want to find out how many times 2/3, 1 time, 2 times, and then 3 times. So we're getting this same exact idea, and we can see that over and over, no matter what tool you use or what you're doing. And so when we're thinking about multiplying and dividing fractions, multiplying is kind of like dividing, because you're cutting it into those equal pieces, and dividing is we're looking for how many times does the divisor go into the dividend. And we see here both of these examples are how many groups. Can we think of an example that would be dividing by fractions for how many in each group? Or do we just see this one interpretation applying to fractions?